Hey everyone, hi, this is Nick. Welcome to my thesis defense. You don't see me yet, you will. But we're going to start off with an introduction from my advisors. So give me 1 second here and I'm going to flip over to their video feed and I'll let them say a few words.
All right, so hello everyone. My name's Francis Nimmo, and I hope you can hear me. Nick, give me a thumbs up if you can hear me. Okay. Okay, so like I said, I'm Francis Nimmo, and I'm one of Nick's thesis advisors, and it's a pleasure to welcome you to Nick's defense today. I wish we could be doing it in person. It's a lot more fun that way. Maybe we can have some kind of celebration when the pandemic is over, but for the moment, we're having to do it remotely. I wish it were otherwise. Just to let you know how this will work, there'll be a public session which will take about an hour or so. So Nick will give a talk, and then there will be public questions. And then the end of that public time, Nick and his committee will disappear into a different Zoom room, and there we will do a private interrogation, as it were. So that's the way it will work. So I was thinking about Nick, and one of the things that really struck me was that he was older than most graduate students entering our program, and he had had, I would say, a fairly varied life experience. So, for instance, he has a rather impressive command of the regulations concerning firearms, for instance, which is not many graduate students have. I think one of the consequences of that is that Nick is basically unflappable, and so that's something that's served him in very good stead during his PhD, that really things don't perturb him, and graduate school can be a stressful time, and so that's been a huge advantage. Nick scored an early success by getting a NASA fellowship, which has given him a great deal of freedom during his PhD, and so he did something unusual, which is he did two very different projects with two very different advisors. And so you'll hear about both of those projects this afternoon. And that shows his versatility. The other thing that I would highlight is that he's really a coding whiz. I'm in the Stone Age as far as computers are concerned. Nick definitely is not. And in fact, one of my colleagues had a similarly Stone Age code, which Nick very generously agreed to take over and move into the modern era. And so I'm sure she's extremely grateful for that. So it's been a great pleasure working with Nick. And now I'd like to hand over to Xi Zhang, his other advisor, to say a few words.
All right. Hi, everyone. Welcome to Nick's thesis defense. And Nick arrived at UC Santa Cruz basically at the same time as me. So I really deeply appreciate Nick for trusting me to give him a very challenging research project, which is doing the atmosphere dynamics on Jupiter. It was so challenging. To give you some reference, the only published model of the mid-atmosphere of Jupiter was 30 years ago. So Since then, we have a lot of observations and a lot of theories, but no one actually trying to simulate them numerically. And it's very hard. But I'm glad Nick actually succeeded. So today, I will guarantee this is the first show of this new tool. I think it's a breakthrough of this field, and it will have a promising future to explore Jupiter. And also, still remember Nick was my TA of the atmosphere class in my first year. Helped me a lot, and I'm still using his homework solutions to guide the students in my class. So thank you, Nick.
Okay, thank you, Francis and She. Let me quit out of Zoom here so it stops stealing my camera and you guys can actually see me. All right. Hi, everyone, from me, and thanks for coming. And thank you for the kind words from Francis and She. This is my thesis defense. So let me introduce, especially if those of you haven't seen me in a while, where I am and what I'm going to be talking about. So this is my defense as a member of the Earth and Planetary Science Department at the University of California in Santa Cruz. Let me real quick pop an interesting image up here. All right. So today, I'm going to be talking about two different research projects I've done. And in the field of planetary science, often we have to kind of become a jack of all trades because of how many interesting things there are to look at, and because of how limited some of the observations are, such that you need to learn a lot of different things to be able to put them together to make sense out of what we have. So here, I'm going to go from planetary origins at the beginning of the solar system, and then to atmospheric dynamics going on at the very present, and nothing in between. So beginning and end. Hopefully not the end. When I started at UC Santa Cruz, I immediately met two excellent grad students, Doug Hemingway and Carver Beerson. And they showed me the kinds of things that they were working on, the variety of interesting ideas they had, and the paths that you could take with our mutual advisor, Francis Nimmo. They had many research projects they were working on involving rocky and icy planets. And after I met with them and Francis and got excited about all the different directions of study that were possible, I then went to talk to Shi Zhang, my second advisor, and we talked about entirely different things, mostly involving atmospheres on gas giants. And after that, I went back and I thought, these are two very different subjects. It's probably too complicated to do both of them. I'm going to have to make a decision. And then I ended up doing both of them. So unlike my wiser planetary grad predecessors who did those multiple projects but then somehow focused them down to a single idea in a thesis, I'm going to talk about both branches of my research in my defense today. And as I was thinking about it, if there's one idea that kind of ties these things together, it's that I study the interesting things that happen to planets when you warm them up. So we're going to be talking about things that can change in the interior and the surface of these planets when they're experiencing heating or anything interesting that can affect what's going on inside them. So let me start with the origin of the Earth and the Moon. I'm going to try to answer questions about the beginning of the Earth, both from modeling and from observations, to get an idea of what happened when they were first starting to form. How did they form? How long did it take for that to happen? How were they shaped by impacts and other events that were occurring while they were building? And finally, and something I'll go into more detail a little bit later, Why do they have such isotopic similarities in the rocks that build them up? The way I'm going to try to answer these questions today is with a chemical isotopic system. Don't get scared by the language, I'll keep it simple. It was active during the beginning of planet formation. This is the hafnium tungsten system, where an isotope called 182 hafnium decays into a very smooth metallic rod. I'm kidding, this happens on the molecular level, one molecule at a time, but this hafnium decays into tungsten. But we have measurements of the end products of this system in rocks from planets that we have today. And by keeping track of its evolution in models of the early solar system that build those inner planets, we're able to say a lot about what happened to the Earth while it was forming and the timing of when these things happened. And I'll do this without ever showing you an isotope diagram. Well, maybe just one, but it won't be bad. All right. First, I'm going to introduce the era of the solar system, where the rocky planets we know today finally came together. Accretion is the word for the process where a planet gains its mass by sweeping up all the other objects in its path around the sun. This is a point in the early solar system where not everything is formed yet. There's still a lot of dust, gas, materials that are unconnected that all orbit the sun. And as a planet grows larger and its gravitational influence increases, it pulls in this material and builds what we see today. Depending on when this build process starts and finishes, when major collisions occur, what kind of material is added, you can get entirely different isotopic signatures in the hafnium tungsten system on the final planet. So how did the accretion process begin? I'll start with a broad picture of how the solar system started so we can get to this planet building stage. The beginning of the solar system was when a nebular cloud of gas and dust was starting to collapse and form the sun. As the material fell inward, because of the conservation of angular momentum, it started forming into a disk. And as this disk rotated, and things inside the disk collided, heated up, small bodies began to eventually form that were gravitationally attracting material nearby. And they grow, maybe into the size of something a few kilometers long in the first 10,000 years, maybe something the size of the moon by the first 100,000 years, and maybe something the size of Mars by the first million years. We're going to call these bodies that have gotten big enough to be about Mars size, which is somewhere on the order of 1/10 of the mass of Earth, planetary embryos. By the point we've gotten to the growth of these planetary Mars-sized embryos, again, we're at about 1-2 million years from the beginning of the solar system. And maybe tens or so of these embryos are still around in the inner solar system, starting to sweep up what's left of the material. And there's maybe hundreds of what we call planetesimals, which are smaller bodies that haven't grown as much as those, that could eventually collide into these embryos. And these things all evolve as the solar system is still turning and everything is orbiting the sun, and we have to let them sort out their problems. So I'm now going to need to explain what happens to these planetary embryos that becomes planets when they're going through the last phase of accretion and starting to crash into each other. So in this final stage here, let me discuss what happens on the inside of those bodies during collisions. What we have on the left is just a homogeneous ball of material. And the reason I have this is because when a small body starts growing, it's literally just a pile of dust and metal and material, whatever is sitting in the solar atmosphere, just pressed together through self-gravity. It hasn't really experienced any kind of change that'll make it different than the pile. There is a process that can do that to small bodies. But the thing that we're going to focus on here is when the body gets large enough, at some point, it might experience enough gravitational energy added to it by things falling in that it will melt. When a body melts, you get a formation into a core and mantle because the densest materials sink to the center of the body and the lighter materials stay on top. And this is only possible when this material is no longer solid. It can exchange once it's hot enough in the melted phase. There's two characteristics that can cause elements to be pulled into the core with the metal other than simply density. A siderophile, metal-loving element likes to attach to metals. So when this happens, those will follow the metals into the core. A rock-loving element, a lithophile, will stay in the mantle. And that's important because this hafnium tungsten system that we're going to talk about has these characteristics. The reason hafnium tungsten is such an ideal system to look at these things is because it has a half-life that has a similar time scale to this planet building process. So 182 hafnium decays and becomes 182 tungsten. And what the half-life of 9 million years means is that a piece of material that is made of 182 hafnium, by 9 million years, half of it will have decayed to 182 tungsten. So over several periods of this 9 million year scale, eventually almost all of your hafnium has become tungsten. Because the hafnium is rock-loving, it stays with the mantle material even after a core formation. Tungsten is metal-loving, and if you have a melting event where the tungsten can move with metal to the core, it will leave the mantle. So let me give you a small schematic of how this happens over time with a body. So this is an example of your core forming late. Look at the gray wedge with green dots. That's mantle material with 182 hafnium in it at the start of the solar system. As time passes, this hafnium becomes 182 tungsten, which is the panel where it changes into blue dots. If this is completely finished, you've had several cycles of this half-life such that there's almost no hafnium left. Then you have a melting event that forms the core. Most of the 182 tungsten will go into the core, and you won't have much left in the mantle. Conversely, let's say your core forms early, when your hafnium is not gone yet. So in this bottom panel, second time, we have a core formed. Early on, none of the hafnium has decayed to tungsten. It's still in the mantle. Now, by the end of the accretion period, all of that 182 tungsten is still in the mantle. And we're going to call this, throughout this talk, the tungsten anomaly, which is excess tungsten in the mantle compared to the other kinds of non-radiogenic tungsten that sit there. But you can think of this as, this is a signal of a planet that has produced tungsten in the mantle after its core formation. If you have another core forming event later, you can keep resetting the tungsten so that it goes down. It depends on what kind of collision it is and what happens during the collision. So let me go into a little bit of detail about that. So what I have here is a schematic showing a body on the left. On the bottom, I'm going to advance this through time to give you hopefully an even clearer sense of what happens to these molecules and where they go during the lifespan of a body. Green will be the hafnium tungsten that's about to decay. Green will be the hafnium. Blue will be the tungsten that has finished decaying, that likes to stay with metal materials. The hafnium likes to stay with the rock gray materials. So let me also put in some non-radiogenic versions of these particles so we can see the comparison between the radiogenic ones and the ones that aren't changing with time. So as I advance time, the hafnium just turns to tungsten. You see it happens more rapidly because of within the first half-life, you've lost half of the material. The second half-life, you've lost half of what's left. So it keeps going down as time goes on. But by the end, you've completely gone to the radiogenic daughter product, the 182 tungsten that is blue. Now, let me give you an example instead of a body where this has happened. You've got the evolution for the first 30 million years, and now another body comes in, impacts it, and causes melting and the core to form. So when you heat up, you pull all of your tungsten, regardless of what kind it is, into the core. Now that this has happened, you've produced more tungsten out of the hafnium left in the mantle, but you don't have the original non-radiogenic tungsten. So this is where the anomaly comes from. An important point to remember here is that the event that causes core formation is not necessarily one thing. Sometimes when these bodies are large enough to be Mars size or so, they have gained enough energy to melt. So this might have happened at the beginning of the process when we start these models. If that's the case, that means your first core forming event has pulled all of the boring tungsten into the core, and you haven't made very much of the radiogenic tungsten yet. So that means for these bodies, the radiogenic tungsten can get very high if nothing else happens later to cause more mixing, melting, and for it to go to the core. Large collisions might be able to remove this excess tungsten that appears later in time. That depends on how the mixing occurs. So let me show you how we parameterize something like mixing for something as complicated as planets crashing into each other. So I'm going to talk about the two end members of this case. In the simplest form, you could have something called core merging, which is very little mixing between core material and the mantle material. So we've got our target body on the left, the impactor is the body coming in to crash on the right. In the core merging scenario, basically the dense core of the impactor sinks straight to the core of the target. It interacts with very little mantle material, so there's not an opportunity for that tungsten still in the mantle to latch onto that core material and follow to the core. There's not full mixing there. So in this case, this is a plot of what the tungsten anomaly looks like with an impact like that. At the beginning, on the left side of this plot, you have it increasing with time as the tungsten in the mantle grows. You have an impact which removes a little bit, but then it continues to grow with time as the hafnium continues decaying into tungsten. It doesn't make a huge difference when there's not much material to pull the tungsten in. On the opposite end, we have a situation where the core completely breaks up when it crashes into the target, mixes with the mantle, and almost all of the tungsten that is available to attach to the metallic material can then sink into the core. When you have an impact like this, your tungsten anomaly is increasing with time. During the impact, pulls everything out and doesn't necessarily completely reset it, but drops it very much closer to what it was in the beginning. Then whatever hafnium is left can continue producing tungsten in the core. And depending on when this impact happens, you could see it could have a different effect. If you have an impact far to the right of this plot, late in time, you drop it down and there's not very much left for it to grow. The growth rate is slow once most of the hafnium is gone. If you have your last impact very early, maybe there's still time for a lot of anomalous tungsten to appear in the mantle. So to give a preview, the Earth's tungsten anomaly is not very high. And the challenge of some of early solar system building models is that you have to build the Earth in the right time scale such that your tungsten doesn't become very large at the end of the Earth's lifespan and then doesn't match what we have measured for the actual Earth. So we want to use this tool to evaluate the models we have for building Earth and the other rocky planets at the beginning of the solar system. The way we're able to do this is take what are called n-body accretion models, which have one measurement for each planetary embryo or planetesimal, whatever size body you want to have rotating around the Earth, and you keep track of it gravitationally. As they evolve, they can crash into each other, build larger planets, and eventually, if your model is reasonable, your end result is something that looks like the solar system we have today. So I'm sorry, I did skip one point because it was on a click. When I'm talking about mixing in the future, I'm going to use a value called k. You can think of it on the simplest set of a k equals 0 means there's very little mixing from an impact, so an impact doesn't pull a lot of tungsten. A k equals 1 means there's a lot of mixing. And I'll go into a little more detail about what this might mean physically and which of these is realistic in a few slides. So let's talk about those n-body models that I brought up. You can kind of group these into two broad categories, although there's more that have come out in recent years that are even more interesting. But we're going to evaluate the simplest ones first. The classical model, what you do is you make the outer solar system early and have it look like just like it is now. Jupiter, Saturn, the outer planets are where they are, and you evolve the inner solar system gravitationally and produce Earth, Mars, whatever other material that you're trying to end up with at the end. A different approach to this is the grand tack, which is a model where Jupiter moves in towards the inner solar system while there's still gas. And then when Jupiter and Saturn get close, they reach what's called a resonance. Don't worry too much about this. You can ask me about it later if you're interested. But then they move back out to the outer solar system and eventually end up where they are. The consequence of this model is that it stirs up a lot of orbital variations in the material between where Jupiter and Mars are now. You get a totally different surface density of planets, and this changes how the planets end up forming in this model. One of the original problems with the classical model, it's simple, it's straightforward, it makes sense, is that it tends to make Mars too large. What it does is, because there's more material in each ring as you go out further, the ring that forms the Earth gets an Earth-sized piece of material. The ring that forms Mars makes Mars too large because there's even more material there than in the Earth's path ring. The grand tack removes a lot of that material and lets you build a Mars that is the size closer to what it actually is. Now, these are both theoretical models, right? We want to be able to evaluate them with physical data and observations and see what we can match up to see which of these models is more accurate at building the Earth. What I'm going to do is apply the isotopic model we have to these so that each planet can experience the collisions that change where the hafnium and tungsten are within the body, evolve to the end state, and compare that with observations we have for the Earth to see what kind of model builds an Earth that looks like the tungsten anomaly we see today. If the grand tack is still very unfamiliar, I'm going to show you a quick video of it, but mainly this is to let you see what happens in an n-body model. What's starting here, you'll see the initial position of Jupiter and Saturn as black dots, and many planetesimals and embryos as red dots interior to them. What will happen when I turn this on is it'll go through the gravitational evolution of all these bodies. We're seeing them from the side, looking directly at the disk in their orbital plane. You don't need to worry too much about inclination and eccentricity. You can basically think of them as those go up, orbits are more chaotic and disrupted. So I'll go ahead and start. These codes keep track of the mechanics of each orbit of all of these bodies throughout this several million year time scale in the early solar system. Then eventually, by the end, most bodies have either been ejected or collected to form the planets that we see today. All right, so with that introduction, let me go into what happens in the isotopic signal of the surviving bodies at the end of these simulations. So I'll start with this plot, which on the y-axis on the left, it says mantle fractionation. You don't need to worry about exactly what that means. Think of that as how much hafnium you had to start with. So if you're higher on that plot, you had the potential to make more 182 tungsten throughout this cycle. On the bottom, we have the tungsten anomaly. This is what we're trying to get right. We want it to look like Earth if these bodies have been made correctly. So this is where Earth and Mars plot on this diagram. Hang on, let me put the error bars on there. There's actually a bit of uncertainty in these. But the tungsten anomaly is not all that uncertain. And the Earth, Mars, and what I will show you, the Moon, are all fairly similar in their tungsten anomaly, which is interesting. You wouldn't necessarily expect bodies that finish building at different times and are different sizes with different collisional histories to have the same tungsten. So can the conditions we've set up in these models create bodies that do have this tungsten? So let me put the end member bodies of one of these simulations up here. This is a situation where back that K value, how much mixing is going on during the impact, is maximal. This is a core that breaks apart, does lots of mixing, pulls lots of tungsten. So what you see here, the final bodies in this plot, which are near the Earth, are ones that have basically been able to get somewhere in the realm of the correct tungsten anomaly. Again, this was maximal mixing. And you can also see the color changes depending on how long it took for this body to finish building. And as that increases, you get closer to lower tungsten anomalies. So like I said before, the later that building finishes, the closer you get to a lower tungsten anomaly. Now, what happens if I reduce that amount of mixing that happened during the impacts? So on the right now is an example of where the amount of core that mixes with the mantle is 20% of its mass. You can see there, none of the Earths at the end of the simulation get to, within error, where the Earth's tungsten anomaly is. What this tells you is that the bodies in this simulation must finish fast enough that you need stronger mixing, more tungsten being pulled out, to be able to bring those anomalies down to the observed levels. So I've just said the planets with fast build time struggle to reduce the anomaly. Lower K, meaning less core material spreading out in the mantle during impacts, is less ability to remove the tungsten. Now, rather than showing you every one of these plots, let me just tell you that it's very difficult for these grand tack simulations, which are what I'm showing here, to produce Earths with the correct tungsten anomaly if K is any lower than 60%. So what does that mean in the context of the other models and everything else? Well, let me show you what classical models on average are able to do. So the classical models, ones where Jupiter and Saturn don't move, are shown here with the tungsten anomaly on average for those bodies on the left and the amount of mixing we had, K, on the bottom. What you can see here, the Earth is the dotted line, the correct Earth is the dotted line on this plot, that the classical simulations are able to get closest to the core equilibration somewhere around, closest to the tungsten anomaly, the correct tungsten anomaly, when the core equilibration K is somewhere around 40%. So 40% of the core material in the impactor splitting up and interacting with mantle material. The grand tack simulations, as I just showed you on the previous slide, this value that is ideal for building the Earth is higher, much closer to 80 or 100% of mixing. So the problem that the grand tack has is that there is no yet experimental or modeling evidence that shows you should expect this amount of mixing. The details for this are fairly complicated and involve fluid dynamics, so I'm not going to talk about them in this talk. You're welcome to ask me about it. But in short, experiments in the lab of metal and silicate materials mixing and simulations of collisions that use multiple particles to simulate melting as best as we can with resolutions probably still not strong enough to really get to the physical details of what's going on. Both of them suggest that impacts shouldn't expect K to be higher than about 20%, maybe 40%. So it's very unlikely that the grand tack requiring this high amount of mixing is going to correctly build the Earth. Now, why is the grand tack failing to do this? I've sort of given you a preview. Maybe you already know, but let me explicitly point it out. The most important factor of the differences between these two are how long they take to build the Earth. On average, the classical models take somewhere around 70 million years before the Earth has its final large impacts, whereas the grand tack model, because of that increased activity in the part of the inner solar system near Mars, basically build the Earth in closer to 35 million years, so maybe half the time. And let me give a direct demonstration of why the time matters. I'm going to show you on the left a plot of how often we get Earths correct in a comparison of the classical and grand text simulations. And on the right, I'll show you what it looks like if you make the grand text simulations happen twice as long in time rather than their normal timescale. So on the left, the black line are the classical simulations, and they are the ones that most often get the Earth correct when equilibration is lower, near 0.2, near 0.3. The grand text simulations need the K equilibration to be higher. You can see that the peak is somewhere between 7 and 8, 0.7 and 0.8. That's what we saw before. On the right, if the only change I make to the grand text simulations is that every collision that happens at twice the time it originally did. So if it happened at 1 million years, now it happens at 2 million years. All of a sudden, it looks like the same distribution as the classical simulations. So it's the timing of building Earth that controls how much mixing you need to get the correct tungsten anomaly. And since experimental and modeling suggests so far that you're going to get a low amount of mixing with these collisions, that's a better sign for the classical simulations because it's much harder for the grand text to build the Earth in those situations. If mixing is at 0.4, you have less than a 2% chance to build the Earth correctly in the grand text model. You will note that no matter how ideal the situations are, it's still fairly unlikely to get the Earth correct. Although something in the vein of 10% right is the best that any of these models do. This can the actual values can depend on a lot of things. There's errors in the exact measurements of Earth mantle tungsten anomaly. There's assumptions made, but 10% is a value where we're saying that might be reasonable. Maybe your model can do this. 10%, 8%. When you get down closer to 1%, that's a problem, and that is also going to come up in the next stage that I'm going to talk about, because now I'm going to introduce what happens when we start looking at the Earth and the Moon together. Now, the Earth and the Moon share similarities in a very interesting set of elements. Right here, and this is the one isotope plot I'm asking you to let me to get away with, we've got comparison of two different types of oxygen in the Earth and the Moon, not just in the Earth and the Moon, in the mantles of many different bodies in samples that we've recovered. What you can see, TFL, the terrestrial fractionation line, is where every sample that we've taken of the Moon and the Earth lies on with these ratios of oxygen isotopes. You can see all the triangles, which are HED meteorites, all the Martian samples we have plotting completely different lines. Basically, every body in the solar system has a unique signature of these isotopes and many of the other isotopes listed here, except that the Earth and the Moon look nearly identical for these listed materials. Now, your simple explanation for this is that, okay, they look the same, they were made out of similar things, maybe. Maybe the environment that they formed in, because the Earth, is at distance of 1 astronomical unit from the sun, is building material there. Maybe because the Moon ended up orbiting the Earth, it was also built of material in that same region. So maybe just those things in that region have the same isotopic relationship with these values. But you should immediately be questioning, why does tungsten do this? Because you've just seen from the hafnium tungsten system that I showed you before, the final tungsten is going to change based on the collision history, what time the core formed, not just what material did we start with. So because of this, now you should be questioning, what is the explanation for why the Moon and the Earth are the same? Can the Moon and the Earth be the same just because they came from the reservoir of a similar material, or is a more complex explanation needed? So there are multiple theories of how we get a moon, but in this instance, I'm going to start with the simplest one, the classical model, where the Moon mostly forms from material of the final impactor into Earth, the last giant impact. If you look at the schematic on the right here, you have a body comes in, strips off material, which mostly reaccretes into the Earth. Material from the impactor is flung off, reforms into the Moon that we see today. This is the basis of many moon models. There are variations, interesting ones, that I'm not going to get into in this talk for reasons of time, but I will look at this model through the lens of our hafnium tungsten system to see if this is a realistic way to get a moon that has a tungsten anomaly like the Earth. So here I'm showing you the final Earth tungsten anomaly versus the final moon tungsten anomaly for many different simulations. These are both the classical and Grand-Tact simulations. On the left, I'm showing you a lower mixing of K equals 0.4. On the right, I'm showing a higher mixing of K equals 0.8. What you want to look at are the intersection of the two gray bands, because the gray bands represent the measured amount of the Earth's final tungsten anomaly versus, I'm saying this, the Earth's final tungsten anomaly is horizontal. The moon's final tungsten anomaly is the vertical gray bar. And if you look at the intersection of those, that's where the real moon and Earth are. So if you're building these correctly, your final bodies should be in that box. And you can see in either of these, there's maybe one, probably less than one, for these actual results. And just from this overview, you can see there are few simulations where an Earth and a moon at the end have very similar tungsten anomaly. So what are the exact chances of this happening? Let me show you a little bit of probability. What you're looking at here, start at the bottom left of this plot. We've got cumulative probability on the right. So as we travel to the right on the plot, each time a body has gotten to a certain amount of closeness of mantle tungsten anomaly. So on the bottom, as we travel towards the right, you are getting closer, you are getting further from an Earth and Moon tungsten anomaly being the same. The dotted line that is vertical shows where if you cross beyond that, you are beyond the current measured uncertainty of difference between the Earth and the Moon. So by the time we've reached not matching the Earth and the Moon, regardless of different setups and different simulations that are on different lines over here, we have not gotten further than about a 5% chance to make a moon that looks like the Earth in tungsten anomaly. That's over all these simulations. There are over like 200 different simulations, some of them duplicates, that are done with these n-body formations. And basically, through the statistics of all of those, we know with fair certainty that it's just very unlikely to build this moon. If you remember, it was already fairly unlikely to build the Earth, and this is on top of that. So the 5% chance to get the moon right is on top of an already 10% chance to get the Earth right. The first thing I would say if I saw this is, okay, that's the classical way of building the moon. The impactor, the body that came in, forms all the material of the moon, and that's what you're trying to get the tungsten to match. I already kind of led into that you should expect that to be difficult. They had different collisional histories. They finished building at different times. What if you cheat a little bit and add some of the Earth material into the moon? Maybe the moon's not totally made of the impactor. Maybe the moon got a little bit mixed during that final impact, and some of the Earth material came in. Well, what we've shown in this paper is that even if you start mixing 10%, 20%, 30% of the Earth's mantle into this body, you start climbing from our initial 2% for these simulations when you were with no Earth material up to somewhere around maybe 10, 15% chance, even if you're building it with half of the Earth material. So the simple explanation that you're just pulling the material from the moon, or even pulling some of the material from the moon and the Earth, seems very unlikely to get the tungsten anomaly correct for the moon. So the ultimate conclusion here is that this classical model of forming the moon might not be the best explanation for the similarity in the tungsten between the Earth and the moon. Let me wrap up some of these ideas into one final point. So first, forming the Earth quickly requires very high mixing K between the core of the impactor, and the mantle of the target to have any chance of getting the tungsten anomaly right. And it's still fairly unlikely, even if everything is lining up correctly. What this means is that models that take a short time to build the Earth, like the Grand Tack, are always going to have a problem getting the tungsten right, assuming that our measurements, laboratory experiments, and models showing that mixing shouldn't be high are correct. Second, forming the moon in the classical sense from impactor material gives an extremely low probability of reproducing the moon's measured tungsten anomaly. So these results favor planet-building models with longer growth times, like the classical model, or variants of it that have appeared in recent years, and disfavor the Grand Tack and the classical model. The reason this was an interesting project to do is because something as simple as one isotope decaying to another was able to give so much constraint on when, how long it takes for the Earth to form, and what becomes of the Earth and the Moon from very little information starting with. We don't have any measurements from that time period. We just have rocks from the Earth and the Moon that we've recovered today, but we're able to estimate what those values were like right at the point that formation was finishing, and we can compare with these models, and just from that isotopic system, we now know what methods of forming these planets were more likely to have occurred. And now we know a little bit more about what might have caused the origins of the Earth and the Moon, and what we should expect to look for. And I'll give you a preview, is that every model we've evaluated, it's difficult to get the Earth, Moon, tungsten right. So it's either an unlikely event that the Earth and the Moon tungsten are as similar as they are, or the complications of putting the Earth and the Moon together in the final impact are far beyond what we originally knew. And some recent models, such as Synestia's, are something that look at these more complicated ways that the Earth and Moon might have interacted. So with that, I am now going to transition into my second project, which goes from the Earth at the beginning of the solar system to Jupiter right now. And this is an atmospheric project, which I worked on with Xi Zhang. So moving completely from the interiors of planets, we're going to the air and the upper outer shells of what's going on. The interesting part of Jupiter is that we know much less about its atmosphere than we know about the Earth. There's fewer observations. The Earth is incredibly studied at very tight detail, and Jupiter is still largely a mystery. Both of them have fascinating weather. You can look at this picture, which is to scale for size, and see the swirls of clouds that we're familiar with on the Earth. You see a similar effect on Jupiter. You can see the banded structure of the white zones and red belts. You can see the interaction between different colors of material. The great red spot, which is as large as the Earth, a giant, I don't want to say cyclonic because it might be anticyclonic, storm that's been going on for decades. The weather on both are interesting, but Jupiter is very different fundamentally. You can see, starting, it's large. It's much further from the sun, so it's colder and receives less radiation. It's made of a hydrogen atmosphere instead of nitrogen. It rotates more than twice as fast as the Earth. So my second project was to build an atmospheric model to explain the interesting weather phenomena in Jupiter's very different exotic atmosphere. So what are the goals of this project? We want to answer these questions. What causes the temperature distribution and wind patterns seen on Jupiter? Where do radiative and dynamical forcing dominate in the middle atmosphere? And I'll explain what those terms mean in a few slides. What is the contribution of different parts of the atmosphere for the radiative heating and cooling? And what does that mean for the subsequent circulation of the air? So let me start. Just take a look at Jupiter. This is the approach of Voyager to Jupiter in 1979, and you can see the dynamics going on in the cloud layer. Basically, what you're seeing happens at a similar pressure to things you're familiar with on Earth. On Earth, the pressure of the atmosphere is 1 bar at the surface, and cloud effects happen on Earth somewhere between 1 bar, 0.5 bar, maybe slightly less than that. And on Jupiter, you're seeing a similar pressure level here. These cloud decks appear kind of at the same pressure. We don't know much about the layers above these clouds, so we want to use a model to understand what dynamics occur there. Our goal now is to model the stratosphere above the cloud layers because of how little is known about that. So what is the stratosphere? What does it look like on Jupiter? Well, this part of the atmosphere of Jupiter can be divided into stratosphere and troposphere. The deeper troposphere has clouds, has convections of air. It's unstable, meaning an air particle that starts the rise there can keep rising or keep falling and have overturn, vertical mixing. And the materials there, because of this motion, are generally homogeneous and spread out. Versus the troposphere is above, where you can see here where the temperature starts inverting and starts growing with height. That is a region of stability because a particle there that starts heating up won't continue to rise. It will stay basically in the same position it is at. Heat transfers there radiatively. So radiation is much more important in the stratosphere than it is in the troposphere. Things can't move as much to transfer heat. Our focus is going to be the stratosphere, but you can see from this figure that it's linked closely to the troposphere. That's why we're going to have to simulate the entire middle atmosphere in one model to be able to explain what's happening. Let me talk a little bit more about why radiation and heating and cooling are important in an atmosphere, and particularly Jupiter's middle atmosphere. Heating from the sun warms gases in the atmosphere. On Jupiter, that means warming of methane and also haze particles that have formed from aerosols into not clouds, but you can imagine like particulate structures. You've maybe seen haze if you've ever seen a picture of Los Angeles or Beijing. On the other side, hydrocarbons like ethane, acetylene, and also the haze particles cool to space by releasing infrared energy that isn't reabsorbed and escapes the planet. If everywhere on the planet heating and cooling were exactly balanced, we wouldn't expect any movement of the air. But you know that the atmosphere is in motion. So the imbalance of the heating and cooling is an important driving force for the circulation in the middle atmosphere. We're going to call this radiative forcing. Just in case you're not familiar with the idea of cooling in the infrared or cooling to space, here's an IR picture of Jupiter. What you can see here, this is Jupiter emitting in the 5 micron band. This is actually cooling from the lower atmosphere, where near the cloud layers, things can get very warm because of material upwelling. But the point I want to make is radiative forcing is an important factor we have to keep track of to model Jupiter's atmosphere. But it's not the only thing we have to keep track of. The next thing I want to talk about are the actual dynamics and motion of the wind itself. So let me start with the simplest case to give everyone a clear overview of what can happen in an atmosphere. Let's imagine a non-rotating planet, not heated at all, everything is the same temperature. In that case, air does not move. You just have a ball of gas sitting inside of your planetary shell. But every planet in the solar system is heated by the sun, and sunlight is most direct at the equator. So this is going to cause more heating there than in other places. Heating causes air to rise and move, creating the circulation cells that you see here. Unfortunately, planets are more complicated than this. They also rotate. So when you start spinning a planet, a particle that is moving towards the pole from the equator also feels the Coriolis force. So it would effectively deflect its path if it were trying to travel in a straight line. The result of this on the Earth is that you form multiple circulation cells instead of a simple equator to pole pattern. This motion is in the troposphere, So we're not talking yet about what could be happening in the stratosphere, but this is more what we're familiar with weather patterns on Earth. If you rotate even faster than Earth, you could imagine that more circulation cells would appear. And on a larger planet like Jupiter, where rotation is faster, you can start to see the results of this. Let me go back to a picture of Jupiter to illustrate. So you see the banded structure here of different colored clouds at different levels of Jupiter. You can translate this idea broadly into the idea that because of the rotation, there are more circulation cells and a more complex circulation pattern at the tropospheric level. You can also see, looking at this picture, that things are kind of smoothed out in an east-west direction. If you go across the planet horizontally in latitude, things don't change nearly as much, in longitude, I'm sorry. Things don't change nearly as much as if you travel vertically on the planet in latitude. To first order, Jupiter is fairly homogeneous in the longitude, the east-west. So usually for observations and discussing what's happening in a broad sense, we also average across longitude. And we're going to call this the zonal mean. In this talk, if you hear me say zonal, that means things in the east-west, crossing longitudes direction. If we want to make a plot of this, so we take an average of the entire sphere, put it into a box, and maybe we want some depth too, so we don't just see things at one pressure level, we see it at multiple different pressure levels. You take this average, you flatten it, and what I'll be showing for the rest of this talk in a zonal mean sense is that latitude on the x-axis will be plotted against pressure on the y-axis. Let me show you an example of what an observation in this case looks like. So this is an example of zonal mean temperature, again with pressure on the y-axis, longitude on the x. Here what you're seeing are the temperature contours of the middle atmosphere of Jupiter. The stratosphere basically begins around the 0.1 bar line, which you can also see is the coldest part of this temperature map. You can also see that there are fluctuations of this temperature in latitude. You remember that there was banded structure across Jupiter when you saw at the cloud level. And here you can also see in the troposphere something is different as you move across latitudes. These fluctuations are going to give us a hint at what the dynamics in this part of the atmosphere are like. And our model's goal is going to be to try to reproduce these fluctuations to get the dynamics correct. Let me show you what the wind pattern derived from this temperature can look like. So the zonal wind can be estimated from the temperature. The relationship between these two is the thermal wind relation. Explicitly, what it means is the vertical wind shear, which is the change in the zonal wind with height, is related to the change of the temperature in latitude. There's a more complex explanation for this, but it has a lot of keywords. You can ask me about it, but for now, just accept that change of wind in height is going to correlate with change of temperature in latitude. You can derive the plot on the right from the temperature on the left. Now look at the plot on the right, which is the wind structure as estimated by this relation in the stratosphere of Jupiter. You can see the banded structure at the bottom extends high into the stratosphere. You can see features near the equator of change with height. You can see basically, and let me make a quick point, the thermal wind relation breaks down at the equator. It involves small f in the equation, which is the Coriolis force. And the Coriolis parameter there becomes 0 at the equator, so you can't use the estimation there, it becomes more inaccurate. However, using this kind of relation is the only sense we have from observations of what wind is like in Jupiter's stratosphere. That's why, again, we want to build an accurate model that can give us a sense of which of the forcings we've been talking about influence the circulation and wind patterns and temperature patterns from the limited observations that we do have to explain what's going on in Jupiter's stratosphere. So the model we've developed here is the first model that uses recent observations to look at the dynamics in the stratosphere. As she said in the introduction, The last model to do this is from 1990. It's fairly outdated now. It was using observations from Voyager in the 70s. It had very simple calculations of radiation. It made some incorrect assumptions about radiative timescales. So we're trying to improve on all of those things. I've already explained in the basis of what builds this model is that there are two important kinds of forcing. That's why I introduced radiation and dynamics in the previous slides. We, with this model, are going to evaluate the importance of each one and where they play key roles in the stratosphere to affect the circulation in different locations. We use the most up-to-date methods we have of calculating radiative forcing to produce the results that we are going to attempt to compare to temperature observations. The radiative forcing involves including the heating from the sun, what happens with the interaction of the light with gas, haze, and clouds, and internal heat from the planet, and combines that with the dynamical forcing that I will explain exactly how we parameterize in a few slides, with some observations of zonal wind at the bottom, to calculate the final values of actual circulation, which give us temperature maps and wind in east-west, north-south, and the vertical directions, which will be UVW. Not super important for the rest of this talk, so don't worry about remembering that exactly. Okay. So I've shown this picture before, but I'm showing it again to emphasize exactly what materials are interacting with radiative forces. And here I want to highlight the haze. So the reason I'm bringing this up is we'll see later that haze has a strong effect on circulation. It's mainly produced on Jupiter through auroral chemistry that happens in the polar region. So you get the highest concentrations of haze in the stratosphere there. Let me show you an example of what this looks like. So this is a picture of Jupiter under UV light. And it's very dark in the UV because the haze at the poles is absorbing a lot of it. UV is high energy radiation. It causes a lot of heat in that part of the atmosphere. Jupiter's poles are much warmer than what you would expect if you model them without haze. So that's the radiative side of the model. The dynamical side of the model are solving the equations of motion. I'm not going to bore you with the details of the equations. You're welcome to ask me about them later, but there's one thing I want to highlight. So forcing in the momentum equation. This is the key part that we can examine by varying the amount of mechanical forcing, dynamical forcing that we use in the model. Here, we're going to parameterize this as a simple drag on the zonal wind, so the wind traveling in the east-west direction. Real mechanical forcing involves waves, eddies interacting with the mean flow, forces from the deep troposphere. This is very complicated and not fully explored yet on Jupiter, so we're starting with a simple setup that is similar to what the older models use so we can evaluate that as a test. Let me show you what this model produces. So what I'm going to show are our model output on the left and observations on the right. On the top, we have the zonal mean temperature. Again, our model on the left, observations on the right. And on the bottom, we have the zonal wind. Observations on the right, our plot on the left. Let's start with the upper left plot. So this is the temperature from our best case model with the mechanical and radiative forcing setup that I've described before. We see in this temperature plot, we do have some fluctuations of temperature with latitude. You can see that at the 1 bar level, at 10 bars, that the temperature is changing as you go across the latitude. We also see we have some influence of heating at the poles. There's hot spots near 3 bars at both the south and north poles. Look down below that in the lower left plot where we see the wind. We see that we have also produced a banded structure throughout the troposphere, throughout the upper troposphere at the bottom and the stratosphere at the top of the wind. So qualitatively, we're matching the main features that we want to match on Jupiter. But obviously, Jupiter is more complicated than this simple model we have. So let's look a little closer at some of the quantitative results and see what features of Jupiter's stratosphere we're not capturing yet and what we might need to change to get closer to the observed values. So let me zoom in. This is at 1 pressure. This is at around 8 bars. Temperature changes with latitude. So this plot shows the simplest possible setup of our model we have. It actually has no dynamics, no drag, no mechanical forcing. This is just the radiative equilibrium model. The main thing to take from this is that you can see the temperature distribution here in the blue, orange, and green lines are smooth. Compare that with the we have spacecraft and telescope observations in symbols. So IRIS is Voyager from the 70s, CIRS is Cassini from 2000, Thesis is NASA's infrared telescope from 2014. You can see in those observed values in the symbols that temperature fluctuates a fairly great deal as you go across latitude. Changes might be as much as 5 or even 10 degrees Kelvin in difference from the mean value. Whereas the radiative equilibrium model, which you see in blue, does not have almost any fluctuations in the mid or low latitudes. At the high latitudes, really only changes because of the influence of haze. I'll talk about that a little bit more later. Even if you take into account the uncertainty of the important hydrocarbon heating and cooling constituents of the atmosphere, which in this case are ethane and acetylene, so that's why I have the orange and green lines. You can see if you change the values that you use in the model by about 20%, which is how much they can vary on Jupiter and a representation of their uncertainty, you definitely still don't get the kind of variations you see in the temperature and latitude in the observations. So let's introduce the mechanical forcing and see what that does to let us match the temperature. This is the temperature plot at 50 millibars. The blue line is the model I showed before, the simple radiative model with no dynamics. The orange, green, and brown lines are variations of models with drag. In these cases, the drag either is prescribed uniformly throughout the atmosphere or the timescale changes with height. The key takeaway here is that drag is going to cause more fluctuations in the temperature as you travel across latitude. You can see that all of the colored lines start to have variations closer to what you would see in the temperature observations as symbols. The reason for the increased variation is that the drag is causing the zonal wind to have a larger vertical wind shear. More drag at the top of the model means the wind slows down, so vertical change in wind speed. If you remember the thermal wind relationship, you can imagine that those changes in wind speed with height lead to greater latitudinal temperature gradients. But you can also see it's not quite fully there. This is why, from this result of the model, we think the simple drag mechanical forcing is no longer enough. To get the actual temperature fluctuations you see on Jupiter, you're going to need to include realistic waves that come from tropospheric convection, modeled similar to the way they are in Earth models, and you're going to need to launch those waves into the stratosphere to cause the kind of fluctuations you see in the observed symbols here. But the mechanical forcing isn't the only thing that's important. We've been talking about radiative forcing. So where is that important in this part of the atmosphere? Let me move to a model that evaluates the influence of haze cooling. So in this case, we're going to focus on the polar regions. And what I have here are experiments with variation on how much haze cooling effect there is. The reason we have these variations is because it's very uncertain what the haze optical properties are for cooling. In this case, from the upper left, I have double the influence of haze cooling, the nominal case. On the lower right, half of the nominal case. And on the bottom, no haze cooling at all, just haze heating properties. And the differences that you can clearly see are the changes in temperatures at the poles. Look at the 2 times temperature plot. There, the hot spots at the poles are much smaller. You have increased cooling influence in the upper stratosphere, and the cold temperatures, the basically blue contours, extend higher into the atmosphere. Conversely, look at the bottom right figure. You have very large hotspots with drastically increased temperature, temperatures that are more than 30 degrees hotter than the 2 times cooling model. If you have a lot of warming at the poles, that change in temperature is also going to have an effect on the circulation. So let me show you a general idea of the way the wind is changing in the atmosphere with a plot of the stream function. So the point of this is that the haze properties are influencing circulation. These are meridional circulation cells, meridional being the equator to pole direction. The flow of atmosphere on these plots basically follows the contours you see. So you can imagine the wind moving in that direction. Red lines are clockwise, and my camera may be mirrored, so I apologize if I'm rotating my hand in the wrong direction. Blue lines are counterclockwise flow. When you have the different polar haze radiative properties, you can significantly influence this pattern, and you can see these two are different. So the normal haze cooling plot on the left basically has broad motion from equator to poles. Things just slowly move from equator towards pole. There's a little bit of overturn and difference at the bottom near the troposphere. But look at the plot on the right. Here you can see at both poles, there's definitely changes in what the circulation cells do. So look at, say, 60 degrees or so north. Because there is very little or no haze cooling there, there's going to be excess heating. And you can see the plot where the lines diverge are where air is rising up, and it's creating two cells, one going towards the pole and one going back towards the equator in the blue. You can see this happens in more than one place in the northern hemisphere and also happens high in the stratosphere in the southern hemisphere. This tells us that the fairly unknown optical properties of haze are going to be very important to nail down to determine the circulation. Because we don't have well-constrained observations of the haze both in distribution and optical properties to know what the haze cooling should be in the polar regions, it's going to be very important to get better characterizations to finish these results. So let me summarize. The model we have built can qualitatively explain Jupiter's temperature pattern and most of the wind pattern. However, it's not finished in terms of incorporating every kind of forcing and accurate results to get very close to the quantitative values of Jupiter's temperature fluctuations in latitude and wind speeds. There's two important components to the atmosphere that I've gone over multiple times in this talk: the radiative forcing and the mechanical forcing. We demonstrated the importance of the mechanical forcing in temperature fluctuations in the mid and low latitudes, and the radiative forcing when it comes to the influence of haze at high latitudes. That means in the future, we're going to want a more complicated construction of the mechanical forcing to capture the very strong variation of temperature that we see in Jupiter's mid-latitudes. Eventually, we're going to need a parameterization of wave forcing that is similar to the kind of forcing that influences these sorts of temperature structures on Earth. On the radiative side, the polar haze properties are important enough that we definitely need, one, more accurate observations of the distribution and optical properties, and two, maybe even experimental data to give us an idea of what these haze particles should look like. Ultimately, to this model, we'll want to add photochemistry, which will involve the using the circulation to move the important hydrocarbon constituents of heating and cooling so that we can self-consistently solve for their influence on radiative forcing in different parts of the atmosphere as they move. So with that, I will pause for a moment to allow any questions to come into the chat that I'll be able to answer. And I'll take a quick section to the personal side of the end of this talk to talk a little bit about the people that brought me here. And I'll let you, if there's anything you'd like to ask, you're welcome to type it in now and I'll try to answer. The first people to thank, obviously, are my two advisors I've had here at Santa Cruz. I looked for every picture I could find on the internet of these two gentlemen, and this was it. And I was like, maybe there's a certain age where we all started posting our pictures online, but they've done an impressive job of keeping embarrassing pictures of themselves completely off of the internet. But both of these professors influenced my learning, the way I do research, how I think about science greatly. Francis actually recruited me from a video chat call. He was traveling to a conference when I came to visit Santa Cruz, but it was successful enough that I ended up coming here. And his skill in planetary science, his openness to looking at any question, his guidance to everyone in my office and planetary group has been immense. And I'm always impressed just how much science he's able to do at any time of the day, is able to effortlessly think about what he's working on. And he's shown me so many things that are interesting to investigate in planetary science. She has given me so much of his time to understand the complex mathematical, scientific, every computer formulations of what you need to do to model atmospheric dynamics. He's put so much effort into this complex subject that I was actually able to work on it on top of the things I do with Francis involving the Earth, which is amazing. I really appreciate the way he's helped me develop my scientific thinking, my editing skills, and how I approach a complex problem. I can't thank either of these people enough. Also, the other faculty and staff of the EPS department, every single person I've ever interacted with, it's been an amazing experience. Everyone in the planetary group, all of the teachers that teach Earth science. Special thanks, of course, to Amy and Jennifer. They are our amazing staff at the front office. Every graduate student, if you take one thing away from this, become friends with Amy and Jennifer. They are everything to getting important administrative things done in your graduate studies. They're amazing. Thank you. Also, the collaborators I've had, people in other departments, Jonathan, people I've worked with on the papers I've done, Rebecca and Seth, and other advisors. Everyone has been amazing in developing the essence of becoming a scientist at UC Santa Cruz. I want to thank all of the students in the graduate department. Everyone here is so enjoyable to be around and generally so positive, and sharing the experience of being a grad student, both the happy things and the difficult things, that every interaction with them always makes it easier to keep working. All the people here, be they Earth science or planetary, are all people I hold in my heart, and I'm glad for every interaction we've had. Finally, I want to thank my family and friends back home who have been waiting while I am across the country. They all live on the East Coast. I've been out here in California for 6 years, and I greatly appreciate their patience and support. Everything I've achieved and where I am is because of them. So thank you in particular to my immediate family, my parents and my sister. And most of all, my partner, Xiaochu, who has been incredibly patient with me while I'm mostly out here away for the last 6 years and studying even years before that. I'll be very glad to get back and spend more time with them, but I thank them all for their support during this. Okay, let me have a look at the questions and see if I can answer anything. Let me scroll back through here. All right. Okay, I'll start with Kobe. Can a synestia give you really high Ks? So the synestia is kind of post-K. The high K is what would be happening when the impactor material, in particular the core, is moving through the mantle of the target body. So it's how much that core breaks up and goes apart. The synestia, what is actually happening is an extended envelope, because the impact that causes a synestia has high angular momentum and energy. The envelope of mantle material, both gas and solid, is extending out beyond like the normal rotational boundaries of what the planet would be. And that kind of mixing of the mantle material would give you more of a uniform Earth-Moon mantle rather than the actual process that removes tungsten. So it would be less that you'd get a higher K and more that the material that you're making the Earth and the Moon out of is basically the combined Earth and Moon that has mixed. Carver, is K expected to be roughly the same regardless of impact size? No, you're correct. And however, what you said, Carver says, my intuition is that for giant impacts between protoplanets, the K would be much larger. Weirdly, that's the opposite of the effect. The larger the bodies in the impact, the more likely the core is to just drop straight through into the target core. It's actually smaller bodies that are able to impact at not a direct angle, but maybe coming in at the planet at the side, that then its path through the body is a long path through the mantle that's much more likely for the core to break up there. The large bodies impacts, maybe at most, so far experimentally, looks like higher than 0.2K is very unlikely. Okay, Patrick. If the grand tack was proposed to fix a wrong size Mars prediction, would tungsten anomalies on Mars further usefully constrain the problem? Yeah. However, so we do track tungsten anomalies on Mars. It's not something we've extensively talked about in our papers. You have measured tungsten anomalies on Mars because of these Sherga-type meteorites. The thing is, Mars's tungsten anomaly is not that different than Earth. And Mars finished building very early in the solar system. It's likely that it was done building probably by 10 million years. So there's not a lot of evolution of tungsten that would allow it to drop. So the way we explain that is by saying, okay, that region of the solar system must have started with less initial hafnium. Therefore, regardless of how you evolve Mars, because you're starting with a low amount of hafnium, that's kind of the only way to match the final hafnium-tungsten relationship and tungsten anomalies. So it can be a constraint, but it's harder to look at because the time scale is so much shorter of where things actually change. Let's see. Okay. Huazhi says, how do you parameterize wave activities in your model? So we're not parameterizing wave activities in this version of the model. That's the next stage. In this part of the model, it's just drag on the zonal wind with variations on the time scale of that drag in different parts of the atmosphere. Compared to the Earth atmosphere, we don't know exactly how important wave activity is. Obviously, it's important in the Earth's atmosphere. There's very important parts of the stratosphere where the circulation is strongly caused by gravity waves or planetary waves that are starting in the troposphere, propagating upward and depositing their energy there. You would assume that that's also going to be important on Jupiter. And there's some wave effects that have been studied near the equator that are important. That's hard to model in our model, but we're definitely going to start parameterizing waves to see the influence on the mid-latitudes. Shinting asks, can you talk more about how tungsten is measured on Earth, Mars, and the Moon? And do you assume normal haze cooling to be Titan-Tholen cooling? Okay, yeah, those are great questions. Yeah, so tungsten I'll start with, I already mentioned on Mars, we do it from the Sherga-type meteorites, which are meteorites ejected from Mars and collected on Earth. The Moon, it's a lot of lunar samples returned by the astronauts generally have been the things that have been analyzed. The Earth, so there's plenty of Earth material to look at, but the trickiness of it is, right now, when you measure mantle material on the Earth, it's not necessarily going to have the same mantle signature as something that happens right at the end of accretion, right? There's a process called the late veneer that maybe more material after the accretion phase was deposited onto the Earth that changed the mantle makeup. It's an explanation because of a lot of unusual things that are found in the mantle based on what you would predict just from a ending the accretion phase. So you have to do a correction from the current measurements of Earth, the Moon, Mars, to account for what might have been the late Veneer influence on those. And that's done very expertly by Thomas Kreuer and Torsten Kleine. They know much more about that than I do. It's an interesting geochemical process if you're into that. It's way more complex than what I've ever done with geochemistry. The second question, do you assume normal haze coolant to be Titan-Tholen's properties? So essentially, that's the starting point, right? She did a lot of the work on characterizing the haze in the polar regions of the stratosphere of Jupiter, and the observations of the distribution, first off, are limited, and the observations of the optical properties come from IR pictures of what the haze is emitting. Because we don't know the structure, like you said, haze-Tholins on Titan is kind of where they start, but different studies have varied those optical properties to different effects. There's a study by Sandrine Gerlet that was published last year that they vary the haze optical properties for a one-dimensional model of the, not one-dimensional, but for a non-dynamical model of heating and cooling in Jupiter's stratosphere, and showed that you do vary the temperatures a lot based just on altering optical properties. So you're correct that Tholins are where we've started, and there definitely shouldn't be the endpoint because there's no real reason to think the hazes are exactly the same shape as Tholins. And we'll probably be looking to you to model how those hazes actually form. Okay. Anything else? All right. Final question. Are there or are there not aliens on Jupiter? They'd be very hard to detect if they were there. We're already, having somewhat problems detecting large, giant distributions of haze, and we know mostly where most of the gases at high levels are. If something was alive, also, imagine how dynamic and crazy Jupiter is. Be very, very hard to detect. You can imagine it, though. You're welcome to. All right. Those were all the questions I found. I think that was everything. I guess at this point, I'll adjourn to my committee to let them grill me a little bit more, and I'll thank all of you for coming. It was great to see you. I really appreciate you being here. All right. I hope you have a nice day, and goodbye.